We are very pleased to present to you Dr. Ivan Ulrich. Dr. Ulrich is a former senior fellow for Strategic Security Program at the Federation of American Scientists. He focuses on issues related to nuclear testing and the testing moratorium, proliferation of nuclear weapons and nuclear materials, the structure of future U.S. nuclear forces, and the exciting conventional military forces in the post-Cold War world. His previous work at the Institute for Defense Analysis focused on environmental restorations of lands belonging to the U.S. Department of Defense and Department of Energy. We asked Dr. Ulrich to join us today to educate us on the relationship between the nuclear fuel cycle on the civilian side and the nuclear weapons proliferation issue that is, of course, continues to be of paramount importance ever since the genie got out of the bottle in 1945. With that, I turn you over to Dr. Ulrich. Thank you very much.
Thank you. I'm very pleased I got a bigger round of applause than lunch. So I think, can we turn the volume down on this? I'm afraid I'm going to squeak. Thank you very much for the introduction. And I'm sitting here because I do not have view graphs, so I thought it would be better just to sit. And I'm very pleased with the invitation to come and address you. It's also very humbling to be in very comfortable surroundings in beautiful Vancouver on the anniversary of the great tragedy suffered by the Japanese people. And as you were told, the topic I've been asked to address is not specific to that, the nuclear accidents in Japan, but it concerns the entire global nuclear enterprise, and that's the connection between nuclear power and the proliferation of nuclear weapons. I'm going to give sort of a general description of how it works rather than looking at specific countries, but there is a close and almost inevitable connection between nuclear power and nuclear weapons. Inevitable might mean that the problem is hopeless and we should give up, but it isn't hopeless. It's an important problem. It's worth working hard to avoid. It is a difficult problem, but I added that almost because I think if we can, with careful technical design, with international regulations, and I believe a fundamental change in how we view the nuclear power industry, we can minimize the danger, if not entirely eliminate it. All of today's established or recognized nuclear weapons powers, those recognized by the Non-Proliferation Treaty, completely integrated their early civilian and military nuclear research. And in fact, the military applications came first. The first nuclear reactors were used to produce plutonium for nuclear weapons, and the knowledge gained from that military experience was incorporated later into the first civilian nuclear reactors. The first uranium enrichment, using enormous gas diffusion plants, were built to provide highly enriched uranium for nuclear bombs, and only later low-enriched uranium for nuclear reactors. Unfortunately, this road runs in both directions, and now we're worried about the reverse process, civilian technology being applied to military uses. And the nuclear reactors themselves are not the major proliferation problem. It's the process of making the fuel that goes into the reactors, and sometimes what we do with the fuel when it comes out of the reactors. This whole process from mining the uranium to the disposal of radioactive waste is called the nuclear fuel cycle, and that's what we have to watch. Nuclear weapons can be powered by either uranium or plutonium, and both elements are intimately tied to the nuclear fuel cycle. Uranium, as we've learned earlier today, is a naturally occurring element. It's fairly common. It's found throughout the world. Canada, turns out, has some of the world's very richest deposits, if not the largest deposits of uranium. And Canada has been and continues to be a major uranium exporter. Uranium, like most elements, I'm giving that a little tutorial this morning, has different isotopes, they're called. And that is atoms with the same number of protons and electrons, so they're chemically almost identical. But they have different numbers of neutrons in the nucleus. That makes them have slightly different weights. And also, putting a different number of neutrons in the nucleus can give typically gives the atoms radically different nuclear properties, even if the chemical properties are the same. So uranium has two main isotopes. There's 235 and 238, and that number just is this total number of protons and neutrons, and is proportional to the weight or mass of the atom. And it's the 235 that powers nuclear reactors, and also nuclear bombs. And unfortunately, I say unfortunately if you're a nuclear reactor operator, the uranium-235 that powers the reactor is less than 1% of natural uranium, 0.7% to be exact. So to be able to get the uranium to react or burn in those common types of reactors, the concentration of the 235 has to be increased above that what is normally found in natural uranium. And this process is called enrichment. So while natural uranium is 0.7% uranium-235, nuclear reactor fuel typically has ranges of 3 to 5% uranium-235. Anything below 20% is called low-enriched uranium, or LEU. And that has, they make a distinction more or less than 20% low-enriched and high-enriched uranium. Those have to be handled very differently because of the security concerns. Many techniques have been used to enrich uranium, but today, far and away, the most popular is to use high-speed centrifuges to exploit the small difference in mass between the two atoms to separate the two isotopes of uranium. So, but uranium-235 is also what can power nuclear bombs. And for that, the 235 ought to be enriched not to the 3 or 5% that you see in a nuclear reactor, but to 80% or 90% or more. Since it's above 20%, it's called highly enriched uranium, or HEU. And that's where the problems start. Because exactly the same pieces of equipment that can enrich to 5% can also enrich to 95%. And when I say same piece of equipment, I don't mean similar technology or machines based on the same principles or built in the same way. I mean exactly the same physical pieces of equipment. Anybody who can enrich uranium at all can get whatever enrichment they want simply by passing the material repeatedly back through the same machines. And unfortunately, the enrichment requirements for needed to produce nuclear weapons are significantly smaller than those needed to power nuclear power plants. So if I build a plant ostensibly to power a large commercial nuclear power plant, I'll have the capability to build roughly 20 nuclear, I'll have the enrichment capacity to enrich enough uranium to build about 20 nuclear bombs a year. And this is why the world is so concerned about Iran's centrifuge program. Iran claims that the centrifuges are entirely for peaceful purposes. Not everybody outside of Iran is fully convinced that that's true. But let's assume that it is true. There's still the problem that Iran could later use exactly those same machines to continue enrichment to levels that could be used to build a bomb. So today, most of the world's enrichment capacity is in those countries that already have nuclear weapons. And so we can say, well, that doesn't present any additional proliferation risk of their problem is the countries have those nuclear weapons, not that they might hit them. The big exception is one company, Urenco, that is a Dutch, British, German consortium. Britain is, of course, a nuclear power, and I don't think anybody is particularly concerned about Netherlands and Germany's proliferation threat. But many countries that are interested in purchasing nuclear reactors have also shown an interest in getting enrichment technology and enrichment facilities. Brazil has 3 reactors, 2 operating, 1 under construction, and it has developed its own uranium enrichment capacity. Jordan and Japan have made it clear that they would like to at least consider the preliminary stages of talking about getting nuclear power plants, and they've made it clear that they would like to at least have the option for uranium enrichment. And Jordan and Japan are not 2 countries that we think of as particularly technologically advanced, but they want to be able to enrich uranium. And saying no to these countries now is very difficult because all of the countries with established nuclear power industries want to pretend that enriching uranium is just another industry, like steel or oil refining. But remember, the equipment that's used to enrich the uranium from power plants is exactly the equipment that could be used to make the stuff of nuclear weapons. And highly enriched uranium can be used in the very simplest possible bomb design. It's called a gun-assembled bomb. The other approach is what's called, a lensed implosion bomb, and that is technically a greater challenge. Gun-assembled bomb is the simplest type of bomb design. The first bomb used in war over Hiroshima was a gun-assembled bomb powered by uranium-235. And the United States was so confident that it would work, it didn't even test it before using it against Japan. To treat uranium enrichment as just another industry, I think is just crazy. So remember, keeping in mind what we can use this for. Now, a lot of countries make the arguments that they want to have uranium enrichment capacity because they're looking for energy security, they're looking for guaranteed fuel supplies, but these arguments just ring hollow. No nation has energy independence. It's a politically very attractive myth, but it's a myth. Countries that want to enrich uranium, they do not have the ability to build their own nuclear reactors, so they're depending on other countries to provide spare parts and technical support, so they're never going to be independent. Even countries that have nuclear reactor industries are fully integrated into a global manufacturing base. I visited the manufacturing facilities in both Japan and Korea, and the Japanese Japanese manufacturers admit that they depend on Korea for key components to their reactors, and the Korean manufacturers admit they depend on Japan for key components of their reactors. Neither industry is truly independent, and both Japan and Korea depend on technology that's licensed from the United States. I think the world ought to be heading in the opposite direction of treating this as a normal commercial enterprise. The uranium fuel production, and particularly enrichment, should not be under any nation's control. It should be internationalized. National control just simply shouldn't be considered legitimate. Admittedly, there are some technical and political and managerial challenges. For example, we would not want to have international enrichment centers with an international staff to sort of become graduate schools for nuclear proliferation. You send your guys over to this place and they all learn how to enrich uranium, and then they come back and they start your own enrichment centers. But there are ways around this. For example, we need to have very few countries that maintain the know-how to manufacture centrifuges. And those countries that manufacture centrifuges would not be allowed to enrich uranium. So you'd have to make a choice. Am I going to be a centrifuge manufacturer or a centrifuge operator? A lot of us here know how to operate laptop computers, but that doesn't mean that we know how to manufacture them. The established nuclear powers might even consider schemes like subsidizing enrichment so that any country that opts out is immediately suspect. The cost of enrichment is small compared to the cost of producing electricity with nuclear power, about 4%. So subsidies would not distort the market very much. And every country that has a nuclear power program is heavily subsidized by the government. So one way to put that is to say subsidies to enrichment would not distort the market any more than it already is. So governments balk at taking control of the enrichment industry. This suggestion is always met with accusations that it's simply nationalization, which is politically widely unpopular today around the world. And it's looked at that rather than in commercial terms rather than security terms. But if the will were there, it'd be easy to do based on worldwide production and Western production costs, because I don't get production costs from China and Russia. The global enrichment industry is perhaps $6 billion a year, and according to my unimpeachable research on Google, that's less than half of what the world spends every year on potato chips. The American firm, the United States Enrichment Corporation, has a market capitalization now of only $250 million after its stock has fallen, in large part because it's had a terrible time trying to compete with Urenco. It's come to the United States government saying that they should get some sort of subsidy so they maintain a de domestically owned enrichment company, and they make arguments about energy security. And I just think that that's, if USEC is going to go bankrupt, then the United States ought to let it go bankrupt. In addition, a global consortium creates a positive goal for countries like, the current glaring example is Iran. Currently, the world has left Iran with no option other than surrender, which is very difficult for them to accept, to swallow politically because of their domestic political requirements. So, entering in a truly international consortium as a partner provides Iran with a face-saving way of climb down. And of course, Iran might refuse, but at least in that case, its intentions are clear. I think that Japan can play a role by setting an example. Japan has a well-developed nuclear industry, and at least up until last year, depended heavily on nuclear power. We'll see how that develops in the future, whether Japan goes toward, returns to its nuclear past. But in any case, Japan has only a tiny enrichment capacity, although it had until recently plans to increase that. Almost all of its enrichment capacity it gets buys from foreign sources just through commercial contracts, proving that a very highly advanced industrial country can depend on the international market to provide enrichment. And finally, Canada, which does not enrich uranium, but is one of the world's largest producers of uranium, has a voice in the global uranium market, and I think has the political credibility to speak out about how the global uranium market ought to be organized. So there's a role, I think, there for Canada. One final point on enrichment. There's currently research and development on developing a new laser-based technology for uranium enrichment. I don't want to sound like a Luddite, but I think that this effort ought to simply be stopped. It's not needed. As I said, the cost of enrichment is only about 4% of the cost of producing nuclear electricity, and that's at the bus bar. That's not what you pay at your home. So even if we reduce the enrichment cost to zero, it would not have a big effect on the overall cost of nuclear electricity. And laser enrichment opens up the possibility of very small, essentially undetectable facilities that are able to make highly enriched uranium in a single step, and it would just be a proliferation nightmare, and any potential commercial benefits would be outweighed by the security risks. So that is discussion of what goes into the nuclear reactor. I said the reactors themselves are not really the proliferation problem, but what about what comes out of the nuclear reactor on the other end? So remember I said that uranium has two main isotopes. Everything I've been discussing is really devoted to uranium-235, which is the isotope that is the one that splits in the reactor, releasing enormous amounts of energy. The other isotope is uranium-238, and that's much more stable. When it is hit by a neutron in a reactor, it does not split and produce energy, at least not directly. But some of the 238 atoms will absorb a neutron, so 238 becomes uranium-239, and that converts in the process of nuclear decay to plutonium-239. And that is the other material that can provide the explosive power for a nuclear bomb. Plutonium as an element, unlike uranium, does not occur in nature, but a standard nuclear power reactor produces many tens of kilograms of plutonium per year, at least. Probably 5 or 6 kilograms, depending on your sophistication as a bomb designer, 5 or 6 kilograms of plutonium are required to build a bomb. And when the fuel rod is pulled from a typical nuclear reactor, it's probably about 1% plutonium. So it's important to keep in mind that plutonium is a different element from uranium, has different chemical properties. So while it's a real technical challenge to separate one isotope of uranium from another, plutonium and uranium have different chemical properties, and they can be separated using bulk chemical means. I'm not trying to say that this is easy, because when the stuff comes out of a reactor, it's intensely radioactive, so everything has to be done by robots and remote control. It's not easy to do, but it's easier technically. It requires less technical sophistication than building centrifuges. There is a process that was developed in World War II called the Curex process, and variations on that are what are still in use today. It's true also that the plutonium that comes out of the typical commercial reactor is not ideal for nuclear weapons, but the United States Department of Energy has designed, built, and exploded nuclear bombs using plutonium from commercial reactors. So it might not be ideal, but it does in fact do the job. Of course, the plutonium has to be separated from the used nuclear fuel before it can be used in a weapon. And several countries do this separation. And why? And I think there's the official reason, and there is what I think is the real reason. The official reason is to recover all that energy that's locked up in the plutonium. If you can, it can power a nuclear weapon, true, but it can also be used in a nuclear reactor as a nuclear fuel. If we separated the plutonium through a process that's called reprocessing, and run it back through the reactor, which during the Bush administration, the Department of Energy started calling recycling, as though we were dealing with newspapers and aluminum cans. We could get that energy out from the plutonium. And in fact, the plutonium is an indirect way to exploit that potential energy that's locked up in uranium-238. Remember that more than 99% of the natural uranium is the uranium-238. So if we could get this scheme to work, we could get 100 times more energy out of a given amount of uranium. Alas, there are some technical problems with this approach. As I said, the nuclear fuel is very radioactive, dangerous to handle, and it turns out that it's extremely expensive to try to separate out plutonium. And it is just from a purely commercial point of view, it's always cheaper, and based on some work that I've done, this statement will probably be true for the rest of the century. It's cheaper just to dig fresh uranium. An even greater hurdle is that to really exploit plutonium, you need a different type of nuclear reactor, one that's called a fast neutron reactor. The world has spent probably a minimum of $50 billion on research and development and has never had a commercially successful fast reactor. The Russians do have one that's operating, but it would not come anywhere close to meeting Western safety standards. Several countries have separated plutonium in the past, and France continues to this day, as does Russia, but we know less about their program. And I discussed this a lot in Washington. I talked to congressional offices, and they asked me, well, if plutonium separation is such a bad idea, why does France do it? And the reason has to do with these fast reactors that back in the 60s and the 70s, Britain, France, and the United States had programs to develop the fast reactors and programs to develop the reprocessing to create the plutonium to go into the fast reactors. In all three cases, the fast reactor program failed. And in the United States, we canceled the reprocessing program that would go along with it, its sister program. And someone should write a PhD dissertation on the momentum of bureaucracies. But in Britain and France, they went ahead with the reprocessing program, even though the fast reactor program failed. And as a result, today, Britain has 100 tons of separated plutonium, and the French have 80 tons of separated plutonium. And I'll remind you, you need 5 or 6 kilograms to make a bomb, so each ton might be up to, say, 200 bombs. So the official reason is to extend energy supply, but what is the real reason? I think it has to do with the politics of the nuclear waste problem. Basically, the French are storing a generation's worth of nuclear waste above ground. And again, if they said that, it would be politically unacceptable. But if you get a bunch of guys in white lab coats with clipboards to walk around and poke it every now and then you can call it reprocessing, and that's okay. And so it's a way of allowing them to put off by decades a decision about where to put a permanent geological repository, which you might have followed the great political pain that we went through in a country like the United States, which, like Canada, has large, very sparsely populated areas. Even we had a terrible political time trying to find, and we eventually failed with Yucca Mountain in Nevada. You can imagine how difficult it would be in a densely populated country like France or Japan or Korea. So there's a huge political incentive to put off as long as possible that decision and dealing with that, but at the same time to be able to justify the current operation of existing nuclear power plants. What's most distressing about this reprocessing story is not that Britain and France made this mistake 40 years ago and found themselves at this dead end, but that Japan and Korea want to start off on exactly that same path now. Japanese experience with their large fast reactor has not been good. They've had sodium fires, it's been shut down. It's just recently started at very, very limited, well, up until the earthquake, it was operating at sort of testing levels of huge power. And they were planning on restarting reprocessing. Political opposition in Korea to permanent geological repositories is extremely intense. But it's clear to me, so the Koreans have a desire to sell politically, but nuclear power is very popular in Korea. And so there's this dilemma. So one of the ways they try to square that circle is that they have this political narrative that they're going to solve the waste problem with fast reactors and reprocessing. But it's clear to me that Korea and Japan settle off on this path that 30 years from now, they're going to be where Britain and France are today, with tons of separated plutonium that is a huge danger and of no use. There's one case which Canada might play a role in this in the future. Canada has designed and manufactured and exported these so-called can-do reactors. These are reactors that are of a different design than most of the light water reactors in use in the world today. And they would be ideal for a small nuclear weapons program. As far as I know, there are no current orders for the reactor, although the Canadians would like there to be. I think in large part this is because of the overall collapse of the nuclear reactor industry, but also in part it's because modern centrifuges have now made enriched uranium so cheap that the can-do reactors, which are so efficient with their neutrons can use natural uranium, their relative economic advantage has gone away because of cheap enrichment. So because there are no outstanding orders or requests right now, it's not an immediate problem. But if the market should revive, then Canada has to be very careful that can-do reactors or successors to can-do reactors are sold only with extremely tight control of the fuel reprocessing to make the extraction of plutonium impossible. And with that, I'm done.
Thank you very much, Dr. Ulrich. I should have thought about this, that maybe your talk was not the best talk to have after lunch, because it's really quite nauseating. If you have some questions here?
This is a difficult subject. I'll try to keep it coherent. When we get into reactors that make plutonium or a grade of uranium that's good for warheads, we immediately get into hundreds of layers of security and secrecy. And the program is not the only thing that can be hidden. The finances can be hidden too. And nobody dares question it. So you can build up a layer or an industry of consultants and lobbyists, and the consultants and lobbyists help their political friends to get back into office. Was that enough to be coherent?
No, I take your point that
That's what comes from living in Japan. I didn't see it when I lived here.
I think that what you're getting at is that we have to recognize that because of the grave potential international danger that could be come from this this commercial activity, enriching uranium to put it into fuel science, we run the risk of sort of almost militarizing an important part of our commercial enterprise. You know, is that, then that has to be something that we fold into the cost equation. You know, when you calculate the costs of anything, you should calculate not just, you know, I have to pay you to go dig up coal. You know, I should calculate, well, what is the cost to other people of burning that coal? And I have to pay you to dig up uranium, and what's the cost of that? So those various costs include environmental costs, but they also include security costs. And that's a cost that's imposed to society. I'm not willing to say that it's impossible, but when we do the calculations, we ought to fold that in and consider that as one of the things that we very consciously consider in our cost-benefit trade-offs.
If I could just follow up on that, one of the other aspects of the secrecy that you described applies to protection of workers in the industry. My experience in occupational medicine at the Hanford site points out that over decades, the workers were completely in the dark about the hazards that they worked with, and it was all under the guise of, well, we can't tell you because of national security. Just wondering.
Where does Irene get their uranium from?
I'm sorry, I couldn't hear the
Where
question.
does Irene get the uranium from?
Oh, what about Iran?
Where do they get their uranium? She wants to
Oh,
know.
where do they get their uranium? I think that most uranium has, they just bought it on the international market, and I think most of it actually came from South Africa. But it doesn't make any difference. Uranium, before it's enriched at all, it's not, there's no international control at all. The International Atomic Energy Agency doesn't keep track of it. It's just a commodity that's bought and sold on the international market, like oil. You know, when an oil tanker leaves the Middle East, by the time it gets to Rotterdam, that oil might have been bought and sold 4 times while it's in the tanker. And it's just a commodity, and nobody keeps track. And so to say, oh, well, this was Canadian uranium, or that was Kazakhstan's uranium, it doesn't make much difference. It just goes into this big pool in the world supply of uranium.
Wouldn't it be a great start to control the uranium sales?
It turns out that control of uranium as a non-proliferation effort would be very difficult. In 1945, before in discovery of nuclear power, there was almost no uses for uranium. It was used as a coloring for ceramics and glasses. And it was thought to be extremely rare. And at the end of the war, the United States, we thought we could keep the Russians from getting a bomb because we would corner the world's uranium market. Well, it turned out that because there was no uses for uranium, nobody was looking for uranium. And if nobody looks for it, they didn't find it. Surprise, surprise. As soon as we started looking for uranium, we've discovered that, oh, there's uranium in Kazakhstan, and Canada, the United States, and Russia, in southern Africa, Namibia, and South Africa, and Australia is sort of the Saudi Arabia of uranium. So uranium is widely distributed. There's lots of small mines. It would seem like a feasible idea. In 1945, there was a small deposit in Czechoslovakia, a small deposit in Congo, and people thought that was it. That was the world's supply of uranium. And so we're just going to get that, buy it all up, and then say to the Russians, nah, we got your uranium, you don't have any. But that won't work now.
Yes, Gilder. I'm kind of following this image of highly enriched uranium, low enriched uranium, and enrichment and the transportation of them. And as far as I know, there have been no transportation accidents to date.
There have been no what?
Transportation accidents to date. Is that correct?
I cannot say that there have not been any transportation accidents, but you have to remember, uranium, before it goes into the reactor, it's not especially radioactive, and it's a heavy metal, so it's not like you not want to put this in your breakfast cereal, but it's when it comes out of the reactor, it's intensely radioactive, and that's when it's bad stuff. For example, when I'm working, if I'm handling fuel rods before they go into the reactor. You don't need any particular radiation protection for that. It's not, and people often think, oh, well, they'll use uranium for dirty bombs. It's not a good dirty bomb. You need things with shorter half-lives like cesium and things. But I don't know particularly of any accidents, but I'm certainly not willing to say there haven't been any.
Then on what you said, HEU would not be an immediate danger to the environment?
I don't want to say that. I want to say that people assume that things that go into nuclear reactors are highly radioactive, and they're not until they come out of a nuclear reactor. Uranium is a heavy metal. It is somewhat radioactive. So it's a heavy metal like,
I'm from Northern Saskatchewan.
Oh, oh, I mean, and there's also questions about lifetime exposures, but that's like it is as a heavy metal. Then my concern about HEU is that the bomb design is so easy. I mean, you can take two half critical masses and slap them together and get a substantial explosion that way.
Yeah, and well, I guess what I'm going to is my concerns then is also the safety and of the transportation between the enrichment sites. Like we currently, Canada sends for our radioisotope productions and our we send our refined uranium to Paducah or Paducah in Kentucky.
Yeah.
And there it's gas centrifuge.
Yeah, that's
and then they send back the highly enriched stuff.
Yes.
So that seems to me like a fair amount of transportation with the problems. Now, if we start doing that on an international scale,
I see.
you see where I'm going? Because
point.
that's what you were talking about in terms of making enrichment centers, so to speak, right? So that Iran would then get its enriched uranium from somewhere else. For its
I think that until the uranium goes into the reactor, you can think of it as another dangerous industrial material that should be protected. Once it's the discussion about highly enriched uranium that Canada uses to produce medical isotopes is a different story, and the Canadians are finally coming around and recognizing that they've got to stop that, and there's no reason for that. So they're going to redo that reactor, which is a good thing. And the South Africans have actually led the way in that. They have a similar reactor. They now use 20% uranium. So the Canadians are catching up.
And just point out that there are plenty of scary transportation stories. The U.S. Air Force lost a few bombs.
That's dropping bombs on planes is a different, different story. They've done that several times. They haven't gone off yet.
This is Alex Smith, Radio EcoShock. My concern is that some of the proposals I'm hearing call for big governments to enter into agreements to control radioactive materials. But as we saw in the collapse of the Soviet Union, sometimes big governments themselves collapse, and then we don't have a situation where we can control things, and some people fear that due to economic situations or other reasons, other governments may collapse. So the whole nuclear dream, it seems to me, and I would like to get your opinion, seems to imply that we must have a relative authoritarian, centralized, large government to even undertake this. What would you say?
Right. There is that aspect. I mean, there's been a lot of psychological work on why is it that, at least in the United States, conservatives tend to like nuclear power and liberals don't. And one idea is that it is a technical structure that requires hierarchical control. And your point is very good. For example, when we look at long-term geological storage, one of the requirements is that it not require any maintenance after the first 100 years or so. Precisely for that reason, is that we can't predict there's going to be a United States of America 1,000 years from now, or people are going to be willing to do this. So one of the design requirements is that we put it there and it doesn't need any further human intervention for the next 100,000 years. So people are aware of that issue. I think that what you brought up in the case of the Soviet Union collapsing, who would have imagined that overnight Kazakhstan was the third largest nuclear power in the world, and people were frantically going to their maps and saying, where the hell is Kazakhstan? And so those sorts of things happen. There was, you can even see the apartheid government in South Africa who built a nuclear weapon. Now they were seeing their government go away, and that was their incentive for getting rid of nuclear weapons. They wanted to denuclearize South Africa before it became a majority government. That's something that you have to calculate. It goes to the fundamental question about what are the limits of nuclear power, and is it technical or is it social? I am convinced that I could design a nuclear power plant that could have survived easily the tsunami in Japan had I known beforehand exactly what was going to happen. Right? If you had told me what the earthquake was going to be and the tsunami was going to be, then could I design a reactor that could do that? Of course I could. But now, can I predict what the next disaster is going to be? So this is a question not of the technical limitations of what I can and can't do, but the human limitation of what I can and can't predict.
Yes. Very interesting. I had a question. What's the cost of storing something for 100,000 years or more?
What is the cost?
What's the cost? Like somebody has to come and paint it once in a while, or make sure nobody else got in there, or I just find this quite amazing that we can talk about this and go on nuclear power plants. We need fuel, we need to enrich it, and it's going to be okay when it's enriched, it doesn't cause any problems. But then once it comes out of it, it's quite hot, to worry about it. But really, Finland is building a long-term storage facility, as you may know. First one in the world. It's designed to last 100,000 years as a minimum. Actually, it should really last 250,000 years, but the Finnish government just decided on 100,000 years, because I guess that sounds good. But the issue is, what's the cost of doing that? And that's just one little country with one reactor. We got 100 reactors in the United States that are quite old, that are, have so much nuclear waste on site, they don't know what to do with it. No long-term storage facility has been built or is even on the drawing board, so to speak. The cost of that must be huge, horrendous. And that never gets calculated into the cost of the nuclear power, the electricity that people pay. It's the taxpayer that has to pay for it. And future generations to come. I think it's quite arrogant for you to say that, sure, we could build a nuclear power plant to withstand the tsunami and earthquake had you known. What about long-term storage? There's no way anyone could predict whatever geological formation you may choose for a long-term storage site that would be safe for 100, 200, or a million years.
Yeah. The question about cost, we do have some basis to estimate that. For example, we spent about $12 billion on the Yucca Mountain facility, which has not been opened. That's an example of what part of the problem here is that was very much a political decision, because at the time that they made that decision, I don't know if you've ever been out to the area, Yucca Mountain is right next to the Nevada test site. And there's a reason they tested nuclear weapons out there, because it's this totally desolate place. It's one of the driest deserts in the world, and nobody lives out there. And so they thought, oh, this is where we'll put the nuclear waste site. And if you had told people at the time, oh, you have to remember that 20 years from now, the ranking, the head of the Senate is going to be from Nevada, they would have just laughed at you, okay? And then, surprise, the head of the Senate is from Nevada. And he killed it, and Obama killed it. But those were, it was a political decision to kill it in response, I think, to a political decision to build it there in the first place as opposed to someplace else. So, and people are paying for it in the sense that, like in the United States, there's a $1 bill tax on nuclear produced electricity that goes into this fund that's supposed to pay for, that the government uses to pay for long-term disposal. Now, clearly they haven't succeeded in doing that. Okay? The question is that technically impossible or not? And there you get into the things where some people are willing to say, yeah, I can be fairly confident I can go down to Grant, like the Finns are doing, and the Finns aren't building that, the Finns are paying for it. The French company, Arriva, is building it, and they're losing a lot of money on it because of the fixed price contract. Some people say, yeah, I can dig down a couple kilometers in granite, I can dig side holes, I'll put it there, and it's fine. And then other people will say, I simply don't believe that you know enough to say that that's going to be safe 100,000 years from now. How can you even say that? And I think that gets beyond that is a scientific and engineering discussion. It's almost it's a political discussion about how much faith should we have in our ability to predict. And I have to admit, I do not know how to resolve that. I mean, people have different opinions, and if they argue about, whether lead or uranium is heavier, I can tell you a way to get to an answer to that. I do not know a way to get to the answer of can I predict what will happen 100,000 years from now.
We have time for one last quick question. There's a question over here. Sorry.
You made a link between nuclear power and nuclear weapons. Our organization, Physicians for Global Survival, would like to get rid of nuclear weapons. So should we try to get rid of nuclear power, and should we try to go one step earlier and get rid of uranium mining?
When I started at the Federation of American Scientists, a really great professor from Princeton, Frank von Hittel, was the president of our board of directors. And I asked him, I said, Frank, what's our position on nuclear power? Are you anti-nuclear power? And he said, oh, no, I'm not anti-nuclear power, I'm anti-pro-nuclear power. And so the question is, the other side of this that has not been addressed directly is we're concerned about carbon. And nuclear power does represent a way to produce electricity with less carbon than if you do it with coal. And the problem with coal, of course, is incredibly cheap. And so there's some people that say, well, okay, put a $100 a ton tax on coal. And there are people who believe, I'm not yet convinced, that the advocates of, say, carbon dioxide sequestration, they claim even with that, if you put a tax on, not on burned carbon, but on emitted carbon dioxide, I can capture the carbon dioxide and sequester it, and it's still going to be cheaper than nuclear power. So what I would suggest is that we just do a true cost accounting. We set standards for safety. We set standards for security and proliferation. You have to pay the money to make it impossible to do these things I'm worried about, okay? If we're worried about, and then we remove all the subsidies. There are vast subsidies the nuclear industry gets from governments. Everywhere there's a nuclear power plant, there's a government that's helping to pay for it. And to take all those away, in the case of, if you're worried about carbon dioxide, put a tax on carbon and let the market decide. If you do that, my feeling is that nuclear power is gone in that case, that nuclear power would not be able to compete in the marketplace without massive government subsidies. Okay? But I would rather approach it from that view, both from a technical and from a political perspective, than I would to try to ban nuclear power. I'd try to remove all the subsidies for nuclear power, and then nuclear power will just take care of itself.
Thank you very much, Dr. Ulrich.